Assalamualaikum and a very good morning. Today our group will present about the hydroxides, nitrates, carbides and also acids for group 1. First of all, let's go to the hydroxides. Hydroxide is the chemical compound that highly react with metal. It contains a diatomic anion with a chemical formula OH-. It also consists an oxygen and hydrogen atom that held together by a covalent bond. Its function is to carry a negative electric charge. These are some examples about reaction between group 1 and hydroxides, which are lithium hydroxide, sodium hydroxide, rubidium hydroxide, calcium hydroxide and potassium hydroxides. Next, we go to the chemical and physical properties. The solubility. The base strength increased by down the group that cause the compound become more soluble in water by down the group. It is because their first ionization energy are all low. The metals become more reactive and form metal ions increasingly readily down the group. Next, we go to the thermal stability. The compound become more stable down the group with increasing atomic number of the metal. It is because the polarizing power of the cation increases up the group with the smaller ionic radius. Next, all the hydroxides are white, translucent and deliquescent solids. Translucent means it is halfly transparent and deliquescent means it is tendency to become liquid. Next, we go to the synthesis. All alkali hydroxides are formed in the reaction between alkali metals and water. As you can see, we use the example of the sodium. The sodium will react vigorously with water to form the sodium hydroxides and releasing this hydrogen gas. Next, the alkali metal hydroxides also will react with carbon dioxide from the air. As you can see, this equation, the metal hydroxides will also react with carbon dioxide vigorously and left the solution open to the air rapidly to become contaminated with carbonate. And lastly, the concentration of metal hydroxide will react slowly at room temperature with silicate glass to produce alkali metal silicates. Next, the uses of this binary compound. The lithium hydroxide is used to absorb the carbon dioxide in space vehicles. Sodium hydroxide is used for chlor-alkali industry. This chlor-alkali industry I will show you for the next slide. Next, it is used for papermaking industry, food industry to break down the protein and act as drain cleaner. Next, potassium hydroxide is for the production of potassium carbonate and potassium phosphate. And lastly, rubidium hydroxide is used in vapor turbines. This video, I would like to show you about the chlor-alkali process. Chlor-alkali process is the process of industry process about the electrolysis of sodium chloride solution in large scale. Let's watch the video.
This lesson looks at what happens when brine undergoes electrolysis. You may need to look at our lesson, what happens in electrolysis, before going any further. The electrolysis of brine is an industrial process which is carried out on a large scale, but we can look at the process on a smaller scale in the laboratory. Brine is a saturated solution of sodium chloride. We don't want the electrodes to become part of this reaction, and so we use carbon electrodes. From the sodium chloride, we have positive sodium ions, Na+, and negative chloride ions, Cl-. And from the water, we have positive hydrogen ions, H+, and negative hydroxide ions, OH-. When the current flows, you will begin to see tiny bubbles of gas forming at each electrode. Both hydrogen and chlorine gas are formed, but can you work out which electrode produces which gas? Pause the video and see if you can work it out. The chlorine is formed at the anode, that's the positive electrode. Hydrogen is formed at the cathode, that's the negative electrode. Did you get it right? Let's look at what's going on at each electrode. The anode is positive and attracts the negative chloride and hydroxide ions. The chloride ions give up their electrons to the anode and are oxidized to chlorine molecules. 2 ions need to be oxidized to make a diatomic chlorine molecule, and 2 free electrons are produced. The electrons are given up to the anode, and the chlorine gas bubbles up to the surface of the cell. If you collected the gas from the anode in a test tube, then you would be able to see the pale green color of the chlorine gas. It will turn down blue litmus paper red, showing that it is acidic, and then it bleaches it. Well, what about the cathode? It is negatively charged and attracts the positive sodium and the hydrogen ions. The hydrogen ions each gain an electron from the electrode to form hydrogen atoms. Here's the equation. 2 hydrogen atoms then bond to form a diatomic hydrogen molecule, and that's the hydrogen gas given off. The gas here is colourless and can be collected in a test tube. The test to prove that it is hydrogen is done with a burning wooden splint, and you'll hear a familiar pop as the hydrogen burns. The ions left in the solution are the positive sodium ions and the negative hydroxide ions, which combine to form sodium hydroxide. Overall, the electrolysis of brine has produced hydrogen, chlorine, and sodium hydroxide, and so we can write a summary equation. Concentrated sodium chloride solution plus water, when electrolyzed, gives sodium hydroxide solution, hydrogen gas, and chlorine gas. These products are very useful, but the electrolysis of brine is done on a much larger industrial scale. Chlorine is used to kill bacteria, and it is soluble in water. If you've ever visited a public swimming pool, then you'll be familiar with the smell of chlorinated water, and it's also used to sterilize water in the main water supply. What's more, chlorine is one of the main ingredients of bleach, which is used in a lot of cleaning products. But this is only scratching the tip of the iceberg, as chlorine is used to make dry cleaning ingredients, electrical insulators, building materials, refrigerated gases, weed killer, pesticides, and some of the hydrogen in chlorine from the industrial process is combined to form hydrogen chloride gas. It's a rather unpleasant gas, but it dissolves in water to produce hydrochloric acid, which is a very useful acid. It too can be used for cleaning metal, but it is also used for producing chloride salts. Sodium hydroxide is another cleaning product, and the most common use for it in the home is for cleaning ovens and unblocking drains. That's a rather amazing collection of uses from our original brine.
My name is Vimisha Deputy Malasalan. Now I'm going to present about nitrites and carbides. Generally, nitrite is any class of chemical compound in which nitrogen is combined with an element of similar or lower electronegativity. It has an ion radius of approximately 140 pm, and nitrites contain nitro ion and 3-. They are classified into 3 general categories, which are covalent nitrite, interstitial nitrite, and ionic nitrite. Now we're going to look at the preparation of ionic nitrite. The first one is by direct reaction of the element at elevated temperature, which is 500 degrees Celsius. For example, synthesis of calcium nitride. 3 mole of calcium will react with nitrogen and produce calcium nitride. Second, by the loss of ammonia by thermal decomposition of metal amide, for example, barium amide. 3 mole of barium nitride will produce 3 mole of barium hydroxide and 2 mole of ammonia. Thirdly, by reduction of oxide and metal halide in the presence of nitrogen gas, for example, preparation of aluminium nitride. Aluminium oxide will react with 3 mole of carbon and nitrogen gas and will produce 2 mole of aluminium nitride and 3 mole of carbon monoxide. Ionic nitrites also undergo hydrolysis to produce ammonia and the metal hydroxide. Barium nitride will react with 6 mole of water and produce 3 mole of barium hydroxide and 2 mole of ammonia. Now we're going to look at interstitial nitrite. Firstly is by hydrolysis, which is usually very slow and may require acid, as does vanadium nitride, to produce ammonia or nitrogen gas. 2 mole of vanadium nitride will react with 3 mole of sulfuric acid and produce vanadium trisulfate, nitrogen gas, and 3 mole of hydrogen gas. Number 2, nitrites of group 7 and 8, manganese and iron, transition metal, decompose readily. For example, iron nitride, decompose at 200 degrees Celsius. Thirdly, nitrites of group 11 and 12, silver and zinc, are less stable except copper. Dry silver nitride is a contact explosive which may detonate from the slightest touch, even a falling water droplet. Then, let's move on to covalent nitride. It can be prepared by oxidation of hydrogen cyanide. Variety of oxidizing agent can be used, including oxygen, chlorine, and nitrogen dioxide. When nitrogen dioxide is used, the product nitrogen oxide can be recycled and used again to produce reactant nitrogen dioxide. 2 mole of hydrogen cyanide plus nitrogen dioxide will produce cyanide and nitric oxide and water. For physical and chemical properties, covalent nitrites. Boron nitride is colorless, good insulator, and chemically more stable than graphite. For hexagonal boron nitride, it is very slippery solid, and for graphite, it's black in color and an electrical conductor. For interstitial nitride, the physical and chemical properties are they are refractory, high melting point. These compounds are very extremely hard and are usually opaque materials that have metallic laser and high conductivities, and finally is chemically stable. Uses of nitrites. Firstly, silicon and titanium nitrites is used as hard coatings and making cutting materials. Secondly, cubic boron nitrites is used as an abrasive and manufactured for X-ray membranes. Thirdly, silicon nitride is used as a material for engine parts. Fourthly, lithium nitride is used as hydrogen storage as it can absorb the hydrogen. And finally, the hexagonal boron nitride is used in cosmetic products and skincare, and also as a billet and bore lubricant in rifle application. As you can see on the slide, there is an image of hexagonal boron nitride as a billet. Now I'm going to explain to you about carbides. The compound of carbon with other elements of lower or about equal electronegativity are called carbides. Compounds of carbon with metal or non-metal. They are classified into three categories, which are ionic carbides, interstitial carbides, and covalent carbides. Now we're going to look at preparation of carbide for ionic carbide. Firstly is by heating metal or metal oxide with carbon or carbon-containing compounds such as carbon dioxide, carbon monoxide, and acetylene. Barium carbide is obtained by heating beryllium oxide and carbon at 1900 until 2000 degrees Celsius. 2 mole of beryllium oxide plus with 3 mole of carbon will produce beryllium carbide and 2 mole of carbon monoxide. Calcium carbide is also can be obtained by heating lime and coke at 2200 until 2250 degrees Celsius. Oxocalcium will react with 3 mole of carbon and produce calcium carbide and calcium monoxide. Aluminum carbide is prepared by heating aluminum and carbon in an electric furnace. 4 mole of aluminum will react with 3 mole of carbon and produce 4 mole of aluminum carbide. Secondly is by hydrolysis in water or dilute acid and form these different hydrocarbons. So ionic carbides are classified according to the hydrocarbon which they produce on hydrolysis, which is metanites, acetylites, and allylites. For interstitial carbide, these type of carbide are formed by heating metal and carbon. And for covalent carbide, these type of carbide are formed by boron and silicon by heating oxides of boron or silicon with carbon. 2 mole of boron monoxide will react with 7 mole of carbon and produce boron carbide and 6 mole of carbon monoxide. And silicon dioxide will react with 3 mole of carbon and produce silicon carbide and 2 mole of carbon monoxide. Physical and chemical properties. For ionic carbides, these are transparent crystallized substances and do not conduct electricity in the solid state. For interstitial carbides, retain their close-packed structure, carbon are incorporated interstitial sites and very high melting point, and it is extremely hard. For example, carbides of vanadium are very hard. Hence, they are used for manufacturing of high-speed cutting tools. And for covalent carbides, they are thermally stable, high melting point, polymeric, and extremely hard. The uses of carbide. Firstly is tungsten carbide. It's used for making tools and used as jewelry. As you can see on the slide, there is a ring of tungsten carbide. And secondly is boron carbide, used as a shield against radioactive radiation, usually wear by a soldier. And thirdly is aluminum carbide. Is used as a preparation of methane, and calcium carbide used as preparation of acetylene, and silicon carbide used in furnace lining. That's all for me, and I'm going to pass my presentation to Chai.
A very good morning to Dr. Hasmina and all my friends. My name is CHM5 with metric number 206554. So today I will continue to my presentation, which is about group 1 elements oxo acid. So oxo acid also called as the oxy acid. So oxo acid is an acid that contains oxygen, at least one other elements, has at least one hydrogen atoms that bound to the oxygen to form the ion hydroxide and form an ion by the loss of one or more proton in the solution. So today I will cover these 4 types of the oxo acid. The first is carbonate, second is hydrogen carbonate, third is sulfate, and the last is the nitrates. So carbonates, these are the physical and chemical properties of the carbonate. The first is in solubility. It is increased down the group. So that means that the lithium carbonate is less soluble compared to the calcium carbonate is the more soluble. Next is thermal stability. So thermal stability is how the carbonate is stable when they are heated by the higher temperature. So this is more stable compared to the other groups. So thermal stability is increased down the group. That means that the lithium carbonate is less stable, and compared to the calcium carbonate is the more stable. Next, the carbonate will decompose to oxide when it is heated strongly by the high temperature. Next is solid at the room temperature and it's colorless. So we have 3 ways to synthesize the carbonate. The first is sodium carbonate. It's mined from the mineral trona, also called as the sodium sesqual carbonate. Second, the carbonates can be formed by passing carbon dioxide in a small amount into the alkaline solution. For example, here the sodium hydroxide will react with the small amount of the carbon dioxide to form the sodium carbonate and water. Third is the solvate process. So solvate process is the process that to form the sodium carbonates. So solvate process will produce the sodium carbonate and also the calcium chloride as a byproduct. So usually we use the brine to use as the element to form the sodium carbonate. So in brine, it consists of the sodium chloride and the calcium carbonate. So this is the overall reaction of the solvate process, but we cannot directly to form the sodium carbonate by this reaction because the equilibrium is light to the left because of the high static energy of the calcium carbonates. So we have 3 steps to form the sodium carbonate. The first is the brine purification and addition of ammonia. So calcium carbonate will undergo the thermal decomposition to form the calcium oxide and also oxygen, carbon dioxide. So carbon dioxide here will use in the step 2. Next, carbon oxide here will react with the ammonium chloride to generate the gas ammonia. So gas ammonia and the carbon dioxide here will use in the step 2, which is production of sodium hydrogen carbonates. So ammonia and the carbon dioxide will pass into the saturated sodium chloride to form the ion ammonium, ion sodium, ion chloride, and also ion hydrogen carbonate. So after cool below the 15 degrees Celsius, the precipitate of the sodium hydrogen carbonate will form and filter out. Next, ammonium chloride will form as a byproduct and reused by react with the calcium oxide in the step 1 to form the ammonia gas. In last step is the formation of the sodium carbonate. So sodium hydrogen carbonate with then filter out will heat in the furnace about the 300 degrees Celsius. So it will form the sodium carbonate, carbon dioxide, and water. So carbon dioxide here will reuse in the step 2. So these are the uses of the carbonate. The first, lithium carbonate is used in the drug development. Second, sodium carbonate will use in the glass making, pulp and paper industry, silicates, soap and detergent production, and also water softener. Third is potassium carbonate used as the glass making, soft soap production, textile, and also photography chemical. The fourth is the rubidium carbonate used as the glass making and short chain alcohol production, and last is the calcium carbonate used as the production of other calcium salts. Next, we will go to the hydrogen carbonates. So the hydrogen carbonate is less soluble than the carbonates, and it liberates the carbon dioxide when it is heated, and also is solid at the room temperature. So we have 2 types of ways to synthesize the hydrogen carbonates. First is the hydrogen carbonate will form when excess of the carbon dioxide is passed into the alkaline solution. So here the sodium hydroxide will react with excess carbon dioxide to form the sodium hydrogen carbonate. Second, we also can prepare by the boiling of the carbon dioxide through the saturated solution of the carbonate. So sodium carbonate will react with the carbon dioxide to form the sodium hydrogen carbonate. But for this reaction, it will reverse when it's at a high temperature. So it will form back to the sodium carbonate, carbon dioxide, and water. So these are the uses of the hydrogen carbonates. First, sodium carbonate is used as the fire extinguisher. So it's because at the high temperature, it will release carbon dioxide and water to help us to put out the water, to put out the fires. The second is baking. So for example, it's baking soda. Baking soda is a mixture of the sodium hydrogen carbonate and also calcium dihydrogen phosphate. So it will form the carbon dioxide to help us to increase the size of the dough. Next is potassium hydrogen carbonate. It used as the buffer in the wine production, water treatment, buffer in low pH liquid detergent, and also additive in soft drinks. And also the last is the antacid. Next, we go to the sulfate. Sodium sulfate is very soluble and readily to form the hydrates. So sodium sulfate is the byproduct of the production of the hydrochloride from the sodium chloride. So here the sodium chloride will react with the acid sulfate to form the hydrochloride and the sodium sulfate as a byproduct. Next, we also can get the sodium sulfate by the flue gas desulfurization and also manufacture of the reagent. So the uses of the sodium sulfate is processing wood, blood, glass manufacture, detergents, and milk laxative. Last, we will go to the nitrate. So for the sodium nitrate, it is deliquestion. So deliquestion is mean that it will easily to absorb the water in the air and to be dissolved. So sodium nitrate is used in making other nitrates, making fertilizer, and also making the explosive. So potassium nitrate is slightly soluble in the cold water and very soluble in the hot water. So it occurs naturally as a mineral salt battery, and also it used as a manufactured gunpowder, explosive, fireworks, matches, and fertilizer. So that is all from me. Thank you.
Preparation of washing soda and baking soda. Washing soda and baking soda are 2 commonly used compounds of sodium. Chemically, washing soda is sodium carbonate decahydrate with the chemical formula Na2CO310H2O. Baking soda is sodium bicarbonate, NaHCO3. In the laboratory, they can be prepared taking caustic soda, NaOH, as the raw material. The apparatus required for the preparation of washing soda and baking soda is arranged as shown here. Limestone, CaCO3, is taken in a flat-bottom flask. Caustic soda solution is taken in a large test tube. Dilute hydrochloric acid is dropped into the flask through the thistle funnel. Limestone and dilute hydrochloric acid react to generate carbon dioxide gas. Carbon dioxide gas is passed through water to remove the unreacted hydrochloric acid. The gas is now passed through concentrated sodium hydroxide solution till a white solid appears at the bottom of the boiling tube. The white solid formed is sodium carbonate, which is insoluble in water. When excess of carbon dioxide is passed through sodium carbonate, it gets converted to sodium hydrogen carbonate. Sodium hydrogen carbonate, being sparingly soluble in water, can be filtered off to separate it from water. This is a laboratory method for the preparation of sodium hydrogen carbonate. Sodium carbonate can be obtained by heating sodium hydrogen carbonate. Sodium carbonate so formed is dissolved in hot water and heated to crystallization point. Crystals of sodium carbonate decahydrate or washing soda are obtained by cooling.